Okay, we have a fairly straightforward problem looking at us this morning. So this is direct shear. So we have two timber components, almost like a piston configuration, and they're carrying loads in opposite direction, obviously static. And then the question basically looks at the components and says, what is the shear stress at sections AA and BB shown on the diagram if the joint has a width of 125 millimeters into the page? So they're giving us the other dimension. The other dimensions are all shown on the diagram. So I'm going to start off with AA. So let me get my pen up here. And so we're going to look at section AA. And I'm going to draw a quick free body diagram. So just if I were to look at this, I'll just go out here, maybe put a little bit of a stick on it just to show what it is. And I'm going to cut it at the section AA. And so we have our externally applied force at the end. That's 6 kilonewtons, and we can see that we've cut it in two locations. So we have a direct shear at AA in the bottom, not AA, but it's equivalent to the bottom, and then on AA itself at the top. And so that would be VAA. And this is also going to be VAA. We know that from symmetry and everything else. So what I need to do is, of course, solve for V at A, or V on section AA. And that's fairly straightforward almost, right? So some of the forces in the X direction, we'll label that as X. Set that equal to 0. And so that's equal to -2 times VAA plus 6 kilonewtons. And that allows us to solve for VAA to be equal to 3 kilonewtons. And so for us to solve for shear stress, we're also going to have to know the area of the cross section. So let's do that. And we get area of AA. And that's going to be equal to 100 millimeters, which is the width as shown on the diagram, and then the depth into the page as per the question was 125 millimeters, and so that's equal to a value of 12,500 millimeters squared. And so now we're able to solve for our shear stress on AA, and that's always equal to our shear force, in this case on AA, divided by the area of AA. And so we have 3,000 newtons divided by the area of 12,500 millimeters squared, and we get a shear stress of 0.24 megapascal, so fairly low. So we're happy with that. So that's tau AA. And so we have one other part to the question, and that is to look at section BB. So we're going to go about it in exactly the same way. So let's draw ourselves a quick free body diagram, if you will. So it's going to be a little bit conceptual in this case. I want to kind of represent what we have here, and then down, and then that will reflect it, reflect the shape. So in this case, we have our 6 kilonewtons pulling to the right, or sorry, to the left, pardon me. And we have our shear forces on the top and on the bottom. And again, because of symmetry, we know they're going to be equal. So if we label this as our shear force V on BB, then this is also going to be VBB. And we'll identify X. We'll do our sum of the forces in the X direction equals 0. So that's equal to negative 6 kilonewtons plus 2 times VBB. And like VAA, we see that VBB, of course, is equal to 3 kilonewtons. We need our area of BB. So we go over to our diagram, we look, we see it's 125 millimeters in width as per the diagram, with a depth into the page of 125 millimeters. And that gives us an area of 15,625 millimeters squared. And with that, we have everything we need to finish solving the problem. So our tau on BB, or shear stress, is equal to our shear force on BB divided by our area of BB. And so that's equal to 3,000 newtons divided by the area, 15,625 millimeters squared. A little bit more than the area AA, so we should get a slightly lower shear stress, seeing as how the shear force is the same. And we come up with a value of 0.192 megapascals. Tau BV. And that's it. That's the problem. So direct shear is usually fairly straightforward. The key is to draw your free body diagram and to make sure that you can see all of the planes resisting the direct shear, so you get the right magnitude for your shear force in the section. And so those diagrams become really important. So hopefully that was helpful to you, and we'll see you at the next problem.